We're talking here about a population, and we're talking about taking a sample from it and asking ourselves whether any statistic that we develop or make from that sample is a good estimate of the real population mean or whatever. If you take the example of a sample like this, you can see that the mean of it, well, that's 20, isn't it, divided by 4, that would be 5. If you take this estimate, that 4 there, that's another sample, that's going to give you, what is it, 31, and if you divide that by 4, you're going to get 7 3/4, aren't you? And same with x3, you took another one. Now, these are going to give you some idea of what the actual mean is, but if you take the mean of all those means, then it turns out that mathematically you have to be getting the actual population parameter, which happens to be 7.3 here. So we're talking about whether the statistics we derive from a sample are going to be unbiased or biased estimates of the actual population parameter, which, as you remember, is normally written with a Greek letter. And in the case of the mean of the means, it's a very good estimate. It's an unbiased estimator of the actual population parameter, which happens to be 7.3. We might have to do quite a few. Now, I'm hoping that everybody understands quite well this idea here. If you've got all these means from little samples that you've taken, you can be pretty sure they're going to be bunched together much more closely than the data themselves. It stands to reason. And you can see the mathematics in example 6. So the variance of the means is sigma squared over n. Now, normally speaking, and in the simplest terms, the variance is defined as the mean of the squares minus the square of the mean. And if you have a whole population, it's very easy to work all of that out. But when you're dealing with samples and you want to know that the, say, the variance you've derived from your sample is a good unbiased estimator of the actual variance of the whole lot, it's not quite so simple. You can follow the first 4 lines for number 1 and number 2, first 5 lines of the example on page 29 quite easily. But then they throw this in, and it looks very odd, because it doesn't look like the mean of the squares minus the square of the mean at all. But if we just do a little bit of algebra, we can see we've got the sum of x squared over n minus 1 minus n over n minus 1 times x bar squared. Now we can see that if n was, say, 100, then this would be almost, to so many decimal places accuracy, that would be the mean of the squares, because you'd virtually be dividing by n. And once again, if n is very large, then there's not going to be any difference between numerator and denominator, and you've simply got there the square of the mean. So it doesn't look exactly the same, but it's almost the same. The point about this is that if you just worked out your variance from, say you've got 2, 4, 6, 9, 11, and if you worked out the variance of that sample, that would not be giving you an unbiased estimator of the variance of the whole population. But this particular form does the trick, and they've thrown it in without really explaining that, but this is the right form to use when you've got a small sample where it's going to make a big difference. There's a difference between n and n minus 1 that's going to significantly affect that the mean of the squares and the square of the mean. But if you do put it into this form and you work the algebra through, you find out that the expectation or the mean of the sample variances is actually the population variance, and therefore if you take that form to use when you're working with your samples and finding the variances, then you do get an unbiased estimator of the mean, whereas if you just used the standard way, the mean of the squares minus the square of the mean, you wouldn't get it. So a little adjustment has to be made, and that's the reason why on your calculators you've got one standard deviation worked out using n minus 1 and one using n, because one's for the sample and one's for the population. This doesn't make much difference when n is very large. When your sample is very large, it makes a minuscule difference, but this is what you should be using, and it gives you the unbiased estimator.